this. Go. What's that?
So this is probably the least confusing of the math classes.
Right. Okay. All right. Well, let's see.
They should just rename this class matrices.
Right. Well, we're actually going to do a little linear algebra. If I can get the PowerPoint to come up. Okay, here we go. Kinda.
PowerPoint's working.
Hide presenter view. Function of 10.
Can we make it to 2.4?
No. I have the mark on page 68, theorem 2.9. All right. And I think, if I'm not mistaken, this sort of follows from the discovery on the previous page. This now is the theorem that sort of supports that. The inverse of a product. Okay? So let's say that we have two matrices. Oh, let me get my pen. Okay. All right. We have two matrices A and B, and they're both invertible matrices. Okay? Now, invertible matrices, give me some characteristics of them. They've got to be square. Perfect. They've got to be square. Okay? And then there's other things too, but that's one thing. Now, these are both invertible matrices of order n. And what does that mean? They're n by n matrices. Now, if that's the case, that's the given, then this implies that the product is invertible, AB. AB certainly would also be an n by n matrix. Okay? And the product of those matrices is also invertible. And not just that, but also that the inverse of those two, AB inverse, is B inverse A inverse. Okay? What's that?
I think we've already touched on this a little bit.
Yeah.
Because it's, when you have the inverse of a product, it's, or like you do the product and then that inverse would be like taking the inverses of the two products.
Yeah, in the reverse order, right? Yeah. Now, they do actually do a little proof on it, and this proof, and most of these do have, the theorems will have at least a partial proof, or one portion of it will be proved. But this is a pretty, it's sort of indicative of how we go about doing it. Okay, now, what's given is that A and B are invertible matrices of order n. Okay, what we're trying to prove is that the B inverse A inverse is the inverse of AB. Okay, now we're not doing the part that says that AB is invertible. Okay, that was left to another thing, but that the inverse is this. But if we show this is true, then that does show they're invertible. Okay, so here's how they do something like that. Okay, A and B are both invertible. Now, we're saying that AB is invertible also, okay, and that its inverse is B inverse A inverse, okay. So what they're going to do is start with AB and multiply that on the left by B inverse A inverse, okay, because we said that's going to be the inverse of this. So if it is, then the product of this had better be the identity matrix. Exactly. Well, if you go back to one of the characteristics of multiplying matrices that can be multiplied, remember, they were associative. Not commutative, but associative. Inverse matrices are commutative as well, but in general not. Okay, but this is associative. So what we can do is do A times B, B inverse, and we did say that was invertible, so that is legal, times A inverse. What is B times B inverse if it's indeed an invertible matrix? That's the identity matrix. So then you have AI times A inverse, and it doesn't matter which one you do, these you do first. Right, and that will give you A inverse, and guess what that gives you? I. Well, now we've shown that when you multiply this by that, sure enough, you get I. That means that they are inverses of each other. Okay? That this is the inverse of AB. AB inverse has to be that. Okay? And that also then carries with it that AB is invertible because you've shown that there is something you can multiply it by and give the identity matrix. And so therefore it is also invertible. Now, Theorem 2.9 states that the inverse of a product of two invertible matrices is the product of their inverses taken in reverse order. That can be generalized to include the product of several invertible matrices. So if we had, I'll try to get this the same way they do theirs, A1, A2, A3, up to AN. These are all multiplied together, but they also are all invertible matrices. That's what's given. Okay? The inverse of that would then be, what would you guess it would be? Okay. AN inverse times AN minus 1. I'm sorry. Yuck. Right in the wrong place. Yuck. I wrote it up rather than down. Okay. Well, I should have. Well, never mind. Okay. AN minus 1 inverse times AN minus 2 inverse to A sub 3 inverse A sub 2 inverse A sub 1 inverse. Okay. Yeah, that's exactly what you would expect. And they only put one of them in front. And it says, see example 4 in Appendix A. You can go back there and look if you wish. Let's do example 7. So let's erase all this ink. Find AB inverse for these matrices. A is, oops, okay, 1, 3, 3, 1, 4, 3, 1, 3, 4. B, 1, 2, 3, 1, 3, 3, 2, 4, 3. Okay, find AB inverse for those two. There's two ways you could do it. Okay, either multiply them together first and then taking the inverse, or taking the inverse of each and then multiplying those together. About 6 of one, half dozen of the other. Pay your money, take your choice. You've already paid your money, so just take your choice. Which way you want to do it?
I'd say multiply them together.
Okay, let's do it.
It's easier than trying to flip it around.
Okay, so AB is going to be, is what?
It'll be a 3 by 3 matrix.
Okay.
Alright, so first blank top of it.
All right.
1 plus 3, which is 4, plus
10.
Blank below that.
Okay.
1 plus 4 is 5, plus 6 is 11.
Okay. You're doing
The
1
below
plus
it,
4 plus,
going down that column.
yeah, okay, plus 6, right? Okay. You said 11?
Right.
Okay.
And then blank below that would
Right.
be 1 plus 3, which is 4, plus 8, which is 12. 10
Okay.
and 12. Strange.
All right. Strange but true. Okay.
Now the next column
All right.
be 2 plus 9, which is 11, plus 12, which is 23. Right? Is that right?
Yeah, 23 you said?
Yeah.
Okay.
Next, go down.
Down
2
is
plus 12 is 14, plus 12 more is 26.
26.
And then the last one, 2 plus 9, which is 11, plus 16, which is 27.
Plus what was the last you said?
16, 27.
Yeah, okay. I thought you said 15. I thought there's no 5s in here. Okay. What did you say, 27?
27.
Okay.
Alright, and then the last column
Okay.
be 3 plus 9, which is 12, plus 9 more, which is 21.
Got it.
Alright, and 3 plus 12, which is 15, plus 9, which is 24.
24.
Yep.
And,
3 plus 9, which is 12, plus 12 more, which is 24 again.
okay, better be. Okay. Now we got to do the inverse of that. Yeah. So what I'm going to do is lose that line and augment this with the,
Identity matrix 3 by 3. Right?
yep, I3. Okay.
I3, U3.
Yeah, we all three for I3. Okay.
Alright, so we can add row 2 to row 1.
Okay.
Or wait, no.
No.
It wouldn't be. No.
What were you thinking?
I was thinking we could do a negative row 2 plus row 1 and then multiply row 1 by negative 1.
Okay.
And that would give us an inverse
Okay. Now,
blank.
um,
So you would, it would be, you get negative 1 in the first
right.
blank, and then you multiply it by negative 1.
Okay.
Unless
Yeah.
you have a better suggestion.
Well, no, that's about equivalent to reversing the order of the first 2 rows and then subtracting row 2 from row 1. I mean, once you reverse them, then do that. It comes out the same, right?
Switch the first and second row.
Right. And then subtract row 2 from row 1. Yeah. And that does the same thing, right? Pretty much. I don't know if it's...
Yeah, and that's easier.
I think it may be a little bit. So can we do that all at once, or...
Let's just switch the rows.
Okay, so it'll be 11, 26, 24, 0, 1, 0, 10, 23, 21, 1, 0, 0, and 12, 27, 24, 0, 0, 1. Okay?
Now we will add negative row 2 to row 1.
Yeah, right. That's the new row 1.
2. And that would be 10,
Okay.
8, so it'd be 1, right?
Yep.
3, 3,
Say again.
yeah, it'd be 3.
Okay.
Okay, now I'm going to get zeros below it, so that would
Yeah.
be negative 10 row 1 plus row 2, right?
Yep.
And then we can go ahead and do that for the next one as well, negative 12 row 1 plus row 3. Does that
Right.
sound doable? Make sense?
So we're leaving row 1 alone. Okay. Uh-huh. Mm-hmm. What's that?
I said that's a lot of 12s.
Yeah.
Alright, and now we want to get that negative 7 to be a 1.
Yeah.
So,
So I guess you could divide by 7s, and that gives you a lot of really nasty fractions. Or swap those two rows while you're negating the, let's see. What I was thinking of flipping these while also negating this one. So you have 0, 9, 12, minus 12, 12, 1. And then this, leave that one alone, and then add those two, and you get a 2 here. And then you have halves, which are easier to work with than sevens. So it's a little extra maneuvering, but it works, I think, I hope. So I'm going to erase the line before, I think, and because I'm not sure I want to cram all that into that little space I've got left. And I just happen to think, I sure hope we multiplied those first two equations, matrices together correctly. I sure hope that wasn't an error, or else we are in deep trouble. Okay. Now, how many steps you want to do on this? 1. Okay, so 1, 3, 3, minus 1, 1, 0. And flipping up, that'd be a 0, a 2. Oh, that's why I was asking how many steps you want on that. And I'm going to go and write the bottom row. 0, negative 7, negative 9, 11, negative 10, 0. And then, yeah. And 3. No. You're negating the bottom and adding it to the second. Yeah. 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 Right. Okay. And there's no way to avoid fractions here, but they're not as bad as sevenths would have been. Okay. So divide by 2, 2, 2, 2, and 2. Okay? I guess I better write that one out. 1, 3, 3, minus 1, 1, 0, 0, 1, 3 halves, negative 1 half, 1, negative 1 half. And 0, negative 7, negative 9, 11, negative 10, 0.
Okay, now we're going to get a 0 below the 1 and above the 1.
Right. So let me erase this down here. The one thing about this, I don't know how your notes are, this class does use a lot of paper though.
Yeah, a little bit. I've kind of gotten to where I'll kind of just write it like this, and that kind of helps save space because I'm so used to just writing everything right below it.
Yeah.
If I were to do that now, it would use twice as much paper.
Right. Okay.
So what we're left with, you still got that matrix.
Yeah.
Alright, so we want to do negative 3 row 2 plus row 1.
Got it.
And then 7 row 2 plus row 3.
Okay. So I'm going to write down row 2, 0, 1, 3 halves, negative 1 half, 1, and negative 1 half. And our new row 1 is?
So 1, 0.
Yeah.
This is where it gets fun.
Yeah. Minus 9 halves plus 6 halves.
So negative 3 halves.
Right?
Okay.
And 3 halves minus 2 halves. 1 half. And negative 3 plus 1 is negative 2. Right?
And then 3 halves plus 3 halves.
3 halves. All right?
Now 7.
Yes.
0.
Okay.
0. 21 halves minus
18 halves.
3 halves.
3 halves.
This is actually turning out to be pretty neat for corrections.
Yeah. Not as bad as it could be.
No.
Minus 7 halves plus 22 halves.
15 halves. Right?
Yeah.
Right.
Okay, and what? Yeah, that's positive. 15 halves. Got it. Okay.
Now we gotta get, so we can multiple, alright.
Yeah. So,
Get 3 halves to be 1.
okay, so multiply everything. Oh, okay. Okay, you're going to do it all. Okay, let's do that. Multiply this by 2/3.
Yeah.
Right? 2/3. 2/3. 2/3. And 2/3. Okay? And the bottom row becomes, I guess we got to write them all. 1, 0, minus 3 halves. 1 half. Minus 2, 3 halves. 0, 1, 3 halves.
Oh man.
Negative 1 half. What?
Let me ask you something before
What?
we continue doing this. This makes me want to mess up the order of the way we do things. That's
Right.
probably not kosher.
Right.
Because I want to do row 3 plus row
Add
2.
those two together?
Or yeah, well, not that necessarily, because that's going to mess up your zeros, right?
Yeah.
But if you, before we multiply by 2/3,
Oh.
if we added it to row 1 and subtracted it from row 2 and then turned it, multiplied it by 2/3. Because that wouldn't mess with your ones, but it'd mess with everything else.
Right.
So I don't know if you
But
can
that
do
wouldn't.
that.
Okay. All right. that's certainly doable. So let's hold on here a second. Let me erase all that I wrote there. I hope I don't erase a sign. Okay.
Yeah, that's right.
Okay. And then not, well,
Yeah, just everything to the right of it.
okay.
Alright,
Now let's
row
make
3
sure I don't
plus
do anything.
row 1 and negative row 3 plus row 2.
Okay.
Does that seem legal?
Yeah, because that won't mess up row 1 and it won't mess up row 2 because of the 0, 0 there in front.
I just saw that.
So,
It's so
yeah.
nice. I hate to
Right.
mess all this up. You know.
Uh,
But see, it's gonna mess with the right side of that, so I don't know how it'll affect the end
Yeah.
result.
okay. So it makes these look better here, but we've still got, in fact, and then we'll do exactly what we did, and then this column will be fine. But you see, we've got to mess with those anyway, they're going to do. But yeah, doing this makes a 0 here, doing this way you said makes a 0 there. Then we change this, and now we have our identity matrix here. So whatever else this is, that's what we got to have because that's what the answer is going to be.
Okay, so it won't matter if we do this in this order.
No.
Get the zeros first and then.
As long as every step is legal, and this is legal, okay? And I didn't mention to, oh no, you saw, they did take the films off. Yeah.
Yeah,
This
those
is
are all
this is
ours.
our board, yeah. This is our board again. Okay, so we're just going to add row 3 to row 1. Okay, row 3 plus row 1. Okay, and that's 1, 0, 0. Yeah. No, it's not bad.
16 halves, which would be
8,
8.
negative 5.
And 2, or 1. 2 over 2. Oh no, that's 7. Oh no.
Yeah,
I thought that was 1. That'd be negative 4 halves, which is negative 2.
negative 2. All right. Okay, and we'll do minus row 3 plus row 2.
I got that part.
Okay.
Negative 15 halves plus a negative 1 half, that would be negative 16 halves.
All right.
8, negative 8, right?
Mm-hmm.
That'd be 4.
Mm-hmm.
And then it would be 3.
Yeah. Okay.
And then we can go ahead and multiply by 2/3.
2/3. All right. So this will be a 1.
0, 0, 1. And that would be 36.
Oh wait, that's 5.
6/5.
Isn't that just 5? Huh?
Yeah, that's 5.
Okay.
So
And 2/3.
then it'd be 2 or negative 2, right?
Yep.
And then it would be -7/3.
Yeah. How did we wind up with just one fraction there? I hope that's right. And look at what we got. 8, negative 5, negative 2, negative 8, 4, 3, 5, negative 2, negative 7/3.
And we broke the mold too.
Yes. Well, you'll have to sweep it up then. Okay. All right.
Because usually, you know, we do the 1 and the zeros, and then the 1 and then the zeros, and then the 1 and then the zeros. But this time, on the last one, we did the zeros and then the 1.
Yeah, yeah, you mean, yeah, the way of doing it. So, sure enough, that works. As long as every step is legal, you can do it, okay? Be very careful.
Too bad this is a differential equation.
Actually, you're doing pretty well in that too. You're right on top of those too. All right. One important property of algebra of real numbers is cancellation property. That is, if AC is equal to BC and C is not 0, then A is equal to B. Invertible matrices have a similar cancellation property, but be very careful with it. And let's do, whoops, that's not what I wanted. Let's do this one. All right. If C is an invertible matrix, then the following properties hold. Number one, if AC is equal to BC, then A is equal to B.
This works because it's you got the same variable being or the same matrix being multiplying on either side, and
Right.
then also it's not commutative, right? Or well, actually that doesn't matter. It's just the same
Yeah, it doesn't matter, but the thing that's important is that C is invertible. Okay, A and B don't have to be invertible. Okay, in fact, they don't even. C, if it's invertible, has to be square. Now it has to be the right size to multiply by A and B, but notice what that means. Pick a size for C. I don't care. 3 by 3. Okay, so that means A could be a 4 by 3.
It could be anything by 3.
Yeah.
And then B could be.
It has to be the same for those to be equal, so that would have to be a 4 by 3 too. Also, but they don't have to be square. Okay.
It could be square, but they just don't have to be, right?
Right. And what we could do to do that, and I'm stealing the thunder here, multiply this by C inverse, multiply that by C inverse, and then this is A times I times A is equal to B times I. A is equal to B. So once you have C's invertible, that gives you lots of options to do.
I just want to divide out C from both sides. I'm not doing that.
But yeah. In general, you can't, especially if C wasn't invertible. You cannot. It requires that C be invertible. That's the first one. Here's the second one. If CA is equal to CB, again, C has to be invertible, then that implies A is equal to B. And the reason you can do it is that because C is invertible, you can multiply this by C inverse, multiply that by C inverse. This is I times A times B, A is equal to B.
Yeah, what I'm pulling from this more than anything is that you wouldn't be able to say this if CA equals BC. Yeah, you can't.
Definitely not. Yeah. But of course, this requires that. Well, but it would have to be A and B have to be the same sizes, or else this thing right here wouldn't be equal. Okay, it can't be a 4 by 3 and that's a 5 by 3. Yeah, you can do this multiplication, you can do that multiplication, but they wouldn't be equal to each other. If they're equal to each other, that means A and B have to be the same size, whatever that first term is. Here is the second. It's the number of rows, columns that have to be the same. But
They just have to hold the same place in the multiplication.
exactly. Okay. Good deal. All right, and I already gave away how to prove it. Okay. Be sure to remember that Theorem 210 can be applied only when C is an invertible matrix. If C is not invertible, the cancellation is usually not valid. For instance, and this is what example 5 is going to do. No, I'm sorry, example 5 we did a couple pages ago. Last time. Those were not invertible. So you couldn't multiply that by the same size. Yeah. Okay. I don't see a C in that example, so I'm wondering what they're talking about there, but we won't worry with it. It's example 5. it says, oh, it's section 2.2. No wonder I was in 2.2. Okay. No, I'm not turning back that far. Okay. All right, now let's look at systems of equations. For square systems, that's those having the same number of equations and variables, you can use the following theorem to determine whether the system has a unique solution or not. Okay? I think we can do it. Oops. Okay. I think we can do it here. All right. If A is an invertible matrix, then this implies the system of linear equations AX is equal to B. That's the system of equations. A is some invertible matrix, and then have the right number of x's, right side, B, has a unique solution. Okay, given by what? My writing or what? Oh, yeah, right, exactly. X, vector X is equal to A inverse B, vector B.
Because it's kind of like an operation to move a matrix across the axis.
Right.
Because it's going to be the inverse of that matrix.
Right. What you do is multiply both sides by inverse A because it is invertible, so it is legal to do. And the sizes must be this. This is your identity matrix, so that leaves you X, and this leaves you that. So some of these proofs are just, woof, done. Okay.
I could always look at these.
Right. Okay.
Let's do exactly.
Now, one use of Theorem 211 that we just did is in solving several systems that have the same coefficient matrix. You can find the inverse matrix once and then solve each just by doing a simple matrix multiplication. Okay? Now, here's where I hope this isn't too far-fetched of an example. Let's say you're a manufacturing company. You have so much equipment, so much manpower and stuff like this, and you can set up your production to, you know that things work together in a certain way. So in other words, your A is going to be the same, okay? But you could have different targets, okay? Outcomes, exactly. And you're going to say, okay, which is going to be most efficient for me, cheapest for me, so, and just try different things. All you have to do is find the inverse once, and then see how that fits into different targets, different outcomes that you're aiming for, and see which one you like best, So that's really vague, but it's kind of like what they're going to be doing in this one. So oops, why do I keep doing that? I'm so used to it. This. All right. Use an inverse matrix to solve each system of equations. Here's A. 2x plus 3y plus z is equal to -1. 3x plus 3y plus z is equal to 1. 2x plus 4y plus z is equal to -2. Okay? Now notice the equations stay the same, identically the same. So I'm not going to write them down. I'm going to write down equal 4, equal 8, equal 5. Being really lazy. And this will be equal 0, equal 0, equal 0. Okay. What's that?
You're just saving slide space.
That's it. Okay. Right. I'm also lazy. Okay. So what we're going to do here, what would be your approach? We could do Gauss-Jordan elimination on each one of these. Okay.
Why would you want to do that?
We don't. Okay. Now, but here's the point. If you're just doing one, Gauss-Jordan is quicker than doing the inverse matrix.
But
If you do multiple ones of the same thing, then find the inverse first. Then the multiplication of that inverse times your products here, or your results here, that's going to be a pretty easy multiplication to do. So, what would we do first?
we're going to find the inverse.
Yep. 2, 3, 1. 3, 3, 1. 2, 4, 1. Now the bad news here is, say again? Okay.
Let's switch row 2 and row 1.
Actually what I want to do is switch column 1 to column 3. No, but you can't do that. Okay, but that sure would.
What I want to do is switch column 3 or 4, 5, and 6 with 1, 2, and 3.
Yeah, see if that works. Okay. All right. So which you want to do? Swap 2 rows first?
Switch row 1 and row 2. And
Okay.
that way you can add negative either bottom row to the first one.
Oh, okay. All right. Can you want to do that in 2 steps, or can we do it in 1? Okay. So in other words, you're subtracting row 2 from row 1 from row 2, but writing it in the row 1 place. Okay. So that is a.
I'm writing myself. Let's see. So this is going to be easier. That'll be 1, 0, -2.
Wait a minute. Okay. Aren't you flipping those two and subtracting this one from that? Is that what you were saying?
Yeah.
Okay. So in other words, you're subtracting this from that, right? So that gives you a 1, 0, 0, minus 1.
See, I had a negative 1 for some reason.
Oh, I hope I copied it right.
No, you did. You did. I don't know why, but I had a negative number in there. So, -1, 1, 0. Yeah, that's what I got. I'm just.
Okay.
That's good.
And then you copy row 1 into row 2, because we swapped those. And this will be a 2, a 4, a 1, a 0, 0, 1. Okay?
So
Next.
-2, row 1 plus row 2 and 3.
Yeah. Okay. So we're using row 1, so write it down. 1, 0, 0, 1, 1, 0. All right. Wait a minute. I got a 2 there. Is that what you got? All right. Almost the same thing. Somehow I knew that was coming. So we go.
Always pick the wrong one to switch.
Yeah. All right. So let's copy the first 1, 0, 0, negative 1, 1, 0. Okay. And I'm going to subtract the second from the third, but write it in the second place. 0, 1, 0, negative 1, 0, 1. And then write down 0, 3, 1, 3, minus 2, 0. Did I do it right? Is that what you were doing? Huh? That was right? Yeah, okay.
And then we just want to multiply. Right, so 3 row 2 minus row 3.
Yeah. I need
Or
to
plus row 3.
I need to get me some room. So I've got to erase the second line here. Okay. You're probably through by now, but I'm still erasing.
No, I'm not quite sure.
Okay. It's not taking. Okay, there we go. So it's minus 3 row 2 plus row 3. All right. Row 1 stays the same, 1, 0, 0, minus 1, 1, 0. Row 2 stays the same, 0, 1, 0, minus 1, 0, 1. And the new third row is 0, 0, 1, 0, no, 6, right?
Yeah,
6, negative 2, and negative 3.
that's our inverse matrix.
Yeah. All right. Now with this, what we do, and I'm going to cheat some here too, if I can get it to cheat. Okay, here we go. Okay. Okay. I'm going to do this and do my minus 1. I shouldn't have done that. Minus 1, 1, negative 2. And doing matrix multiplication. Exactly. And what will this come out being? Right. Right.
1 minus 2 is negative 1. And negative 6 minus 2 more, which is negative 8. Plus 6 is negative 2.
Negative 2.
2, negative 1, negative 2.
Right. All right. Now I'm going, just because I don't have much room, I'm going to erase the, if you don't mind, erase this.
Oh,
Okay. And plug in 485. And put this answer over here.
that would be -8 plus 8, which is +4.
8, isn't it?
8
I think so.
minus 15, which would be -7.
Okay. sure hope we're doing this right because I'm not checking my answers yet.
I'm writing it all down.
Okay. Oh, I think I can do this one. What you think?
Really? In your head? That quick? Can I guess? Is it 000?
You cheated. Okay.
Oh.
As soon as you saw that one, once you knew, well, once we had established it was an invertible matrix because we found the inverse, that's the only solution you can have.
And they got all the same answers we did.
And they got 2, -1, -2, 4, 1, -7, 0, 0, 0. Good for them. Homework exercises here include any of the odds 1 through 5, any of the odds 7 through 29, at least 7 through 25, and then if you want to try 27, 29, they suggest you might want to use a graphic calculator or a computer program or something to do those. Any of the odds 31 to 35, either 37 or 39 or both, either 41 or 43 or both, either 47 or 45, 45 or 47 or both, either 49 or 51. Those could be a little long, but you certainly can give them a shot. They say use a graphic utility or a thing, but that's up to you. 53, 55, 57, and 59.
So, what about is the biggest matrix?
I'm sorry?
I said, what about is the biggest matrix we'll be doing in this class?
I don't know if there's a limit, but we're not going to do many that are beyond. Most of them are going to be 3 by 3 or less. We will probably do a few. Now, when we get in the next thing on determinants, especially on matrices that have lots of zeros in them, you can do huge ones with those. Okay, because they're pretty easy to do if you have plenty of zeros. One like these, 51, for instance, 5 equations, 5 unknowns. No, 6 equations, 6 unknowns.
6 plus 6.
That's a lot of time, a lot of effort. Okay. And especially it says using inverse matrix. If I were going to do that, I'm going to use graph Jordan elimination. I'm not going to do an inverse matrix with a 6 by 6. But if you had a tool to do it with, that would be a little better. How far did I get? 59, 61. And then there's some true false. Not a bad idea, 63, to think through those, but I don't know if there are answers in the back. And then odds 65 through 71 are all proofs or guided proofs. You can do those depending on whether you want to or not. I'm having trouble breathing. 73 is a writing type problem, so I would say think through that one anyway. 75 actually requires you to have something from 74, so if you want to do it, you can. I'm not going to say you have to. 77 is another proof. 79 is could be an interesting problem. I haven't read it all that carefully. There could be some nuances there I'm not seeing. There's another writing on number 81 or 83. Okay, so it's up to you if you, and if, especially if some of those writing things say, hey, there's something I might want to pursue as a paper, then do that. Now, let's back up to 77. This is something called a householder matrix, okay? I don't think that's the same as someone who likes to play Monopoly and is holding on to their houses or something like that. Or has anything. I have a feeling that's named after somebody. So that may be a potential paper topic there. Okay, so I'll let you look at the rest. Let's move on to 2.4.
Elementary matrices.
Yes.
We're going backwards.
Yes, why do you say, oh, you mean you start elementary and move ahead, yeah. Okay, we'll erase all that ink. I hate to say this, but I may have told you before, I won't go into it now. Okay. I just remember the boards and everything else. One of the emails I had sent, about this, I said, well, I don't do the erasing, so I use ionizing pen, on my tablet. And one of the administrators was like, well, we might want to just look into buying more ionizing pens. Well, wait. You have to have a computer that responds to an ionizing pen. In other words, a tablet computer. You just can't take anybody's laptop and start doing. And so I said, you have to have a computer to do it. So now you're talking about getting people tablet computers with ionizing pens.
Well,
So,
I know, at least for this hallway, like Dr. Thomas and Mr. West, they both have, I'm pretty sure their
Surface Pros.
Pros
Right.
would be responsive to something like
Right. But they have pens with them, don't they? I mean,
I don't know if they come with pins or not. You can
can
always,
you use your finger on them?
yeah.
You can. Okay, well then you wouldn't need a pen. Yeah. So no reason to buy an ionizing pen. You could use a stick. I mean, couldn't you?
The stylus or something.
Yeah,
Or an
exactly.
eraser, like that.
What's that?
Like, turn your pen around.
Right. Yeah. So I don't know why that popped into my head. So let's do elementary matrices. Okay.
Example 1. Definition.
Well, before we get there, Section 1.2 introduced the 3 elementary row operations for matrices. Remember what they were? We've been using them. Switch 2 rows.
Add them together and multiply.
Add a multiple of one to another. And multiply by a constant all the way across. Yeah, exactly. Okay. Now, here's a definition of an elementary matrix. The only reason I do this is, as far as I know, some people may not still have books, or one of the people I think is using a different book trying to hide what we're saying, so put these down there. So elementary matrix, number 1, has to be square. So we'll call it an n by n. Well, let's just say order n. Okay? An n by n matrix is called an elementary matrix. Okay? When it can be, say again? When it can be obtained.
I have a feeling we're going to like elementary matrices.
Okay? Until you see what we're going to do with it. Okay? From an identity matrix. Okay? By a single elementary row operation.
So basically one switch or one multiplication or one addition.
Yeah. Elementary row operation. ERO. Okay.
Looks like GRO, but we'll go with it.
What's that?
It looks like GRO, but we'll go with it.
Okay, make fun of my writing here. Okay, it really hurts. Okay. All right. Which of the following matrices are elementary? Here's A. 1, 0, 0, 0, 3, 0, and 0, 0, 1.
I would say, yeah, that's an elementary.
It is, because you just multiplied one row of the identity matrix by a constant, a non-zero constant. How about this one? Is this an elementary matrix? 1, 0, 0, 0, 1, 0. Why not?
It's not n by n matrix.
Is what?
It's not n by n.
Yes, it's not a square matrix. You have to have a square matrix. Okay? How about C? That means yes in Spanish. Okay. That's a 1, 0, 0, 0, 1, 0, and 0, 0, 0.
Now, here's where I have to ask a question.
Right.
When we get zeros at the bottom, that's a singularity, so this can't be.
Okay. The elementary row operations are...
You can't multiply by a zero.
Right, that's
So
it. It's multiplying a row by non-zero entry.
Right.
And the only way you could get that was multiplying a row of the identity matrix
By zero.
by 0. That's the only way you can get that.
Or it's a singularity and it's just not even.
Right,
Yeah.
yeah. Okay. All right, so that's a no, though we haven't gotten there yet. D is 1, 0, 0, 0, 0, 1, and 0, 1, 0. Yes, that is. You swap two rows. E is 1, 0, 2, 1. Yes.
It would be 2 row 1
Plus row 2. You got it. Okay, and F. 0, no, I'm sorry, 1, 0, 0. I can't write. Ah. Well, here we go, finally. Okay. 1, 0, 0, 0, 2, 0, and 0, 0, minus 1. Is that an elementary matrix? Yeah, you did 2, not 1. Okay. So we had yes, no, no, yes, yes, no. Okay, let's see what they got. The first one is elementary, so the yes was right. The second one's not, okay, because it's not a square matrix. The third one is not because you multiply by a row by 0. You couldn't do that. D was, you just swapped two rows. E was multiplied multiple, you added a multiple of one row to another row, so that was, and F was not because it required 2 elementary row operations to get that result. You can only do 1. Okay, elementary matrices are useful because they enable you to use matrix multiplication to perform elementary row operations, and that's what we're going to show in example 2. How are we doing on time? 12:03. We got, what, 12 minutes? Okay. All right. So let's erase all this. Hunger is setting in pretty seriously here. Okay. Okay. Oh, I think I know what to do. Okay, I believe we didn't have this one, but one similar to it. Is that an elementary row? Elementary matrix? Yes, it is. Okay. We're going to multiply that by any old 3 by 3 matrix. It doesn't absolutely have to be, but this one is a 3 by 3. 0, 2, 1, 1, negative 3, 6, and 3, 2, negative 1. All right. Might look like this is going to be hard. It's not. Okay. What you going to get? 3 by 3. Okay. Okay. Now, I'm asking which one are you doing?
I'm
upper left. Okay, so it would be going like this, right?
Right. So zero times
Zero.
zero is zero.
Uh-huh.
Plus one.
Right.
Or wait, no. Yeah, yeah. Plus one
Uh-huh.
plus zero, which is
Right. So that would be a 1. Now which one? One below it?
one below it.
Okay.
0 plus 0 plus 0, so 0. And then 3.
The one below. Oh, you said 3. Okay, got it. Okay.
Next column.
Okay.
0, negative 3 would be it.
Negative 3, you said?
Yep.
Okay.
Then 1. Then 6. Right.
Okay, I couldn't hear.
That'd be
You're doing the 2, 2.
keep missing.
Okay. This times that. Right? You got a 2.
2, and then 2.
And then what?
A 2.
A 2?
Another 2, yeah.
Yep.
And the last column would be 6.
Yep.
1. Negative.
Got it. Okay.
Oh, I just started going in all sorts of directions.
Okay. Now, notice what you have as your result there compared to your multiplier here,
You just switch the first 2 rows.
which is exactly what your elementary matrix did. And that's exactly what elementary matrices do for you. They do your elementary row operation corresponding to which one did that on the identity matrix, and you do it for this one.
So if I just took, but if you just looked at that and you saw that they switched these 2, you could just easily tell it would be 1, negative 3, 6, 0, 2, 1, 3, 2, negative 1.
Right. Okay. So it's
Okay. So
but it's easier to switch rows than it is to multiply by that, you know.
it is. That's what I'm saying.
But you know, it does that for you. Now, here's another. They claim elementary matrix: 1, 0, 0, 0, 1/2, 0, and 0, 0, 1. Is that elementary matrix?
Yes.
Yeah. Let's multiply it by this, and this isn't a square matrix. It's just one big enough you can multiply by. It's a 3 by something. This happens to be 4. 1, 0, negative 4, 1. 0, 2, 6, negative 4.
Okay, can I take a guess at what this is going to be?
Yeah, I think so. 0, 1, 3, 1. Oh, man. Goodness gracious. He's sitting this long. Okay.
So, would we just half everything in the second row?
That's it. 0, 1, 3, negative 2. The others stay exactly the same. 1, 0, minus 4, 1.
Alright, now how are they
0,
going to
1,
build
3, 1.
on this?
Okay. It's pretty nifty what they do with it. But it's just, okay, it takes lots and lots of space and room. Not that bad, but it's,
A lot of writing.
what's that?
A lot of writing.
Fair amount, yeah. We okay with that?
I don't know. 12, 10.
12:10. All right, we got 5 more minutes. I think we can do C, especially since I think you got a good idea what's going on. 0, 0, 2, 1, 0, 0, 0, 1.
So, multiplying row 1 by 2 and adding it to row 2 is what we're doing.
Right. on this matrix that I'm writing now. Okay.
The result of that would be 1, 0, -1 for the top row.
Good guess. And anything for the bottom?
0, 4, 5.
Okay. And then,
Powers going here.
what's that?
It'd be 2 plus -2, which is 0, right? And then -2. And then 1. And that's my guess. And that's what they got.
All right, good deal. Okay. So you see what it said. But if you did the elementary, and they're easy. I mean, this was really easy. That's a 1. And that's a 5. Okay, so those are easy. And then this one's not bad either. Yeah.
That'd be a -2.
Yeah. And you all.
Zeros are nice in matrices.
Yeah, they make it really easy. It's just that middle row that you do, but when you see it happen, right? Yeah, it's not bad enough. Okay, so yeah, we'll leave that alone. Do I have time to write number theorem 12.2? 3 minutes, okay. So let's clear this and do 12.2. Now it says, be sure to remember that theorem 12.2, to multiply A on the left by elementary matrix, this text does not consider right multiplication by elementary matrices, which involve column operations. Okay, so in each of the 3 products in example 2, you're able to perform elementary row operations by multiplying on the left by the elementary matrix. And here's what this next theorem says. Let E be an elementary matrix. Okay? Obtained by performing one of the elementary row operations on IM. Obtained by performing one of the, or does it just say an, elementary row operation on IM. Okay, so E must be an M by M matrix, by the way. If the same, this is what we're just doing, ERO, elementary row operation, is performed on an M by N matrix A, okay, the resulting matrix is given by EA. Okay, it's not each, it's just EA. Okay, and that's basically what we did before when we were looking at those examples.
And we are out of time.
Yeah, and that is it. Where will we pick up next time? I just had to stand back. This was hurting so bad. Okay. Let me just mention this. Most applications of elementary row operations require a sequence of operations. For instance, Gaussian elimination usually requires several elementary row operations to row reduce a matrix. This translates into multiplication on the left by several elementary matrices. the order of the multiplication is important, the blah, blah, blah. Okay, we'll start with example 3 next time. Yeah, and I'm going to, just for you and them to call out a few homework. There's not many here. Do any of the odds 1 through 7. I think that's all we'll do, 1 through 7. We'll pick up the rest of those next time.